Hi, everybody. Today I have put together a guide for you to help explain some of the difficulties in answering the questions for the classical genetics practice problem set. Today, in this lesson, I'll talk to you about the simple monohybrid cross and the probability questions. And of course, these refer to questions 1 through 10, the first lesson. So one of the things I want you to do in your work here is to show me your work. I don't want just answers. I want to show you. I want you to show me how you got it. When you do your Punnett squares, you're going to have the parental cross and the genotype and phenotype ratios. And of course, for this problem, I'd like you to see your math. Okay, so if a coin's flipped 5 times in a row, the probability of getting 5 heads is. Now listen, what's the probability of getting heads if you flip a coin? Well, it's 1/2, right? There's 1 out of 2 chances for you to get a heads. If the question is, what are the odds of doing heads, 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 heads? Then what I have to do is multiply those probabilities with each other, okay? And so the answer to this problem is 1/2 times 1/2 times 1/2 times 1/2 times 1/2 for a total of 1/2⁵, or 1/32. And you're going to use this type of math to answer the problem sets moving forward. So let's go to a Punnett square. In question 2, they tell you that being weird is dominant to being normal. Now that's an important clue, and you should start to think immediately about what that means. So if being weird is dominant, what letter should we use? Well, it makes sense that we would use the letter capital W to indicate weird. Conversely, on the other hand, I would use a lowercase w to represent normal. So I have these 2 alleles, weird or normal, and then I'm going to use that knowledge to identify the genotypes of the parents, right? The type of genes those parents have. Yeah. So it tells you a heterozygous weird male and a normal female have a child. All right, so the heterozygous weird male, this is the male symbol here, he's going to have the genotype of big W, little w, right? Heterozygote, he's got 2 different copies of the alleles. Mom, on the other hand, is a tough one. Mom is normal. Now remember, normal is recessive, so in order for you to get the right genotype for mom, you got to remember that she's a homozygous recessive form, and that's the normal phenotype. All right, so genotype, genotype little w, and that makes her normal. And of course, this guy's going to be weird. So in order to generate a Punnett square, remember that I want to show all the pairings. I want you to show me the genotype and phenotype classes. That is, like, what are the genotypes present? What are those ratios? And what are the phenotypes present? What are those ratios? So the first thing I do is I draw this cross, right? So this shows me that I've got the normal female, that she's being crossed with a normal male, right? Okay. Well, that gives me this. Okay, I drew my Punnett square, right? And so we're going to say mom's going to be on top of the box every time. Remember that mom makes 2 types of eggs. Both have little w, but she does make some that carry the gene her dad gave her and some that carry the gene her mom gave her. Dad, on the other hand, makes 2 kinds of sperm. Some that his dad gave him, some that his mom gave him, right, for the W gene. And so I end up with these pairings, right? When this sperm meets this egg, I get big W, little w. Same here, down here, the sperm meets this egg, I get the lowercase w, homozygous recessive, heterozygous. And so what I see is actually sort of a replication of the parents, right? I see that big W, little w, the heterozygote, is in a 1-to-1 proportion with the little w, little w. And so we say that there's a 1-to-1 proportion of weird to normal. And that would be the ideal way for you to do your Punnett Square, right? I've got the parental cross here. I've got the Punnett Square. Everything's filled in. And then last but not least, I've given phenotypic and genotypic ratios. So then the follow-up to this question is that if the couple in question 2 has 4 children, what's the probability that all of them will be normal or weird? And so since they're in a 1-to-1 proportion, right, the odds of being normal would be 1/2, right? Right? And of course, if I want to know what are the odds of the first kid being normal, being weird, it's 1/2. The second kid would be 1/2. The third kid would be half, and the fourth kid would be half. To give me 1/2⁴ exponent, or 1/16. Okay, and the odds to being normal are exactly the same. Okay, question 4 is, it's a little more ambiguous. And these problems are really, they're puzzles. Okay, so hopefully you start to build some confidence. Remember that the first thing to do is read the question carefully and get as much information out of it as possible. Sometimes, it's deliberately a little bit confusing, right? I'm not going to ask you if you'll see what you get on the test, but in this question, we say if we cross 2 parents who are heterozygous for a particular trait, what's the probability they have kids or homozygous recessive for that trait? All right, so both parents are heterozygotes, right, for a trait. It doesn't matter what it is. So let's say this, that, let's call it the, what's a good letter? The H trait, and they're a heterozygote. Oh, wait a minute. It's not the H trait. I think it's the S trait. The S trait, and they're heterozygous. What happens when these two get together, right? And you should, hopefully, you guys know the answer almost immediately to this one. Okay, so let's say that we're going to use S's, right? And I'll say that the capital S means you're slick, little s is sick, so both parents are slick, right? And I do my cross here, right? They got heterozygote male, heterozygote female. Look at the contributions, right? And I end up with 3 phenotypic classes, big S, big S, big S, little s, and little s, little s. Now, look, the ratios are, there's one of these and one of these to actually not one, but 2 of these, okay? When we talk about phenotypes, though, right, I just have all 3 of these guys are going to be slick, and with one individual that's going to be sick, right? And so the question is, what's the probability if they have kids or homozygous recessive for that trait, right? So what's the answer to that one? Well, the answer to that one is going to be what? There's a 3-to-1 ratio of slick to sick. The question is, what are the odds of getting 2 kids that are homozygous recessive for the trait, right? So 2 kids that are this grouping here, right? And the odds of having that kid are 1/3. So it's 1/3 for the first kid, 1/3 for the second kid, which is 1/3 squared, or 1/9. All right, well, hopefully you can navigate most of those other problems. Do your best. If you get stuck, you can contact me and I'll work your way through it. Let's finish up with question number 10, right? It says slimy skin's dominance of dry skin. This is essentially the same problem we just did, right? And so both parents are heterozygous. What are the odds of having a dry skin baby, right? And they are going to be what? It's a 1 to 2 to 1 ratio again, right? I got heterozygotes. I get this 3-to-1 ratio. We're talking about this dry skin baby here. What are the odds of having? So it's the odds of having a dry skin baby, again, 1/3. What are the odds of 100 of their offspring will be dry skinned, right? So that asks you to say, like, all right, 1/3 times 1/3 times 1/3. And this is sort of a joke question, right? So et cetera. So that becomes 1 over 3 to the 100th power, all right? Which I wrote down as a gajillion. I don't know what the answer is. I don't care. Listen, hopefully you got it. You know, these problems definitely are something where you're like, don't get it, don't get it, don't get it, and then finally you're like, oh, okay. But they do require a little bit of your attention, and that's why I kind of like them. All right. I'll follow this up with some answers to those questions on incomplete dominance, codominance, sex-linked traits, and multiple allelic problems. See ya.